Morning, folks. Any questions about Lab 4 at this point? We're on the downhill slope, 1 day left. And then Monday is final project start. So by the middle of the week, probably by Tuesday actually, we'll have a new consulting schedule out. And you should look at that. The lab hours will change more or less permanently. All of the labs that are currently there will be there, but the times at which the lab is open will be expanded. So you're going to want to check out the scheduling site on the web page sometime in the middle of the week. Weekend hours are fairly popular, and we'll try and accommodate you on that. And probably not next week, but by the week after, I'll be in the lab most of the time during the day when 2300 isn't there. So every morning. What start time do you like? 8 o'clock's a little early. It's early for me because I have to do a little bit of work every morning just to keep up with email. I could open at 9 or 10. How many people would prefer 10? How many people prefer 9? Oh, it's almost a split. I'll have to figure it out. What's that? 9.
Alternate.
Every other day. On the odd days, we'll open up at even hours, and on even days, we'll open up at odd hours. What? Now, I'll probably aim for 9 or 9:30.
Maybe 9 on Monday and Tuesday, since
Those are shorter days.
43 comes in after that.
Oh, that's a good idea. Maybe
And
9.
after that, 10.
Maybe so. Yeah.
Just after that, like it's pretty much open for 6 hours.
It's SARS for the rest of the week. Any questions about final project? Any questions about ordering parts? That's Monday, 8 a.m. How many people are putting in an order? I've gotten exactly 1 so far. That's Pavel. Nobody else is ordering parts? Well, that'll be easy. All right. Okay, that's cool. Work delayed is work avoided, as Dilbert always says. Yes? You own it. It's on your budget. If you order something through me where it costs real course money, then it is on your budget by default. So think carefully before you ask me to spend money. You can't then not use it. Any other questions about parts ordering or final project logistics or?
If we are intending to rent parts from you, so we have to do that kind of like notify you in advance or just do an app?
No, there's no. If you want to rent parts, so let's say if you want to use a television or something of that sort, no, you just use it, and we'll see what you're using when you do the final demo. No, there's no formal procedure. There are a few parts that are limited. For instance, I have 2 full-color 1.5" LCD displays out of Nokia phones with the drivers attached and everything, so they're actually like usable. If you want one of those, it's first come, first serve. I have about 10 radios, UHF radios, data radios. Again, it's first come, first serve. So they're bulky, but they're an easy radio link. They essentially look like a wireless RS-232. Yes? I see someone. Okay. Nothing else? Probably this afternoon, or maybe next week, maybe this afternoon, it's time to open up the fourth cabinet and allow you to dig through there looking for spare parts. There's 2 or 3 boxes of random parts. Anything you find in there that's in the spare parts, basically the bottom 2 shelves, is not budgeted. So I know there's at least one little keyboard in there, cheesy keyboard. There's a couple old hard drives. There's some power supplies. There's a pile of random integrated circuits. So you might want to take a look through that. So I'll continue on then. If there's no questions, seems pretty quiet. I'll start talk some more about serial communication. So last time I talked about the hardware and indicated that the serial hardware, the RS2, the USART the hardware allows full duplex communication. You have completely independent transmit and receive hardware. And what I may have not said strongly enough is that once you load the output buffer, UDR0, once you load the output buffer, and then that data starts getting shifted out according to the baud clock, that you have about at 9600 baud, you have a whole millisecond while that's being shifted out. So that you don't want the CPU to wait around for that millisecond. That's 16,000 instructions. But so you really do want to set this system up so that it's asynchronous, so that you start a character and then go on and do something else. And I want to talk a little bit about how to organize that. So now getting down to the register level here, there are 2 baud rate registers which you basically have not interacted with, but you could. UBRR 0 L and H, but you can address them all as one, as UBRR 0. And if you want to use some completely custom baud rate, let's say you have 2 of these systems talking to each other, you don't have to talk at any standard baud rate, 9600, 4800, 192, 115200. You could communicate at any baud rate you want, and the value that you have to set UBRR0 to is F crystal over 16 times the baud rate minus 1. So a hasty look at this suggests that you can get up to about a megabit per second if you want. Joe, question?
Yeah, there is a table in the data sheet. It's page 190, and it has all these baud rates calculated.
You memorized the page?
I know that pretty well.
Very nice. I like obsessiveness. Yeah. So
yeah,
so
for 9600 is the number is 103.
yeah, 103. That's right. So but if you want to pump the rate up to a megabit per second, you can do that, but not if you have an indirect connection. If you have a direct connection between 2 MCUs, so transmit goes to receive, receive goes to transmit, and ground, of course, goes to ground. So you have MCU. Then you can set this up probably to a megabaud and it'll work. But if you're going out through a standard RS-232 plug with the 9-pin connector, then that means that you've gone through a level translator, and the level translators are not good above about 38,000 baud. They're limited to something like that. There's, of course, the usual configuration registers, UCSR0A, which has all kinds of interesting information in it, which is not used by, so far, either by fprintf or scanf, printf or scanf, or for that matter by tiny real time. There's a bit RXC0, which actually is used. This is the receive complete. This is character complete. That says that there is something in the receive register worth reading. Then there is TXC, transmit complete, which says that not only that both it says that both entries in the two-entry pipeline, transmit pipeline, are empty. I find that singularly unuseful, but UDRE0, transmit data empty, goes high when one of the two buffers is empty, and therefore it is time to refill it. So this is a very useful flag if you want to have a high communication rate. Unlike almost every other config flag, this is set at reset time. Because after all, the transmit buffer is empty when you reset the CPU. Next bit is frame error. A framing error occurs if the 4 samples of each bit do not match. In other words, it can detect bad clock rate. Next bit is, so this is frame error. Next bit is data overrun. Data overrun occurs if a new character is complete and the transmit complete bit is still set. Reading the UDR, reading the data register, auto clears the read data complete bit. So if this bit is still set, when the next character is complete, it means you have lost a character. So a data overrun error means that that the software has not read the UART often enough to avoid losing data. Next bit is UPE0. This is a parity error. You can turn on parity checking. I haven't bothered to do that ever, but you certainly can do that. Parity error, I think this requires odd parity. There always has to be an odd number of bits in a data frame. This bit turns on U2X0. That's double speed. So when you need to go into warp drive, you put on U2X0 and then it doubles the baud rate. But it reduces the error checking. And so it is easier, it is harder to detect a frame error.
Doesn't this only work for asynchronous?
Only for async. You can put the USART into synchronous mode, and then it becomes another SPI channel. And so this particular device, the USART, can act like a second SPI channel, in which case you now have a transmit line, a receive line, and a clock line. And then the last bit is the multiprocessor MPO M0. It's the multiprocessor bus address mode. Which allows you to connect more than 2 devices to the line and to supports and resolves addresses. I haven't used that much. Then there's another register, the USART which has the enable bits in it, and the only 2 bits that you absolutely have to turn on are bits 1, 0, 1, 2, 3, 4. Bit 3 is transmit enable, TXEN0. Transmit enable. The interesting thing about turning on transmit enable is, of course, first of all, it allows the UART to transmit data, but turning on this bit completely overrides every other I/O function of line D1. So, if you turn on this bit, if you do a UART init, if you turn on this bit, D1 becomes useless for I/O. Some of you have discovered this the hard way. Bit 4 is RXEN0, which is the receive enable. Same thing for that enable. As soon as you set the RX enable bit, you have disabled pin D0 as general I/O, and nothing will work for output except through the UART. There's 3 possible interrupts that you can enable corresponding to these 3 flags. There's a receive complete, RXIE0. It's a receive complete. That says every time that there's a RXCIE, every time there is a character ready to read, the CPU throws an interrupt. There is a TXCIE0, which says that every time both members of the queue of transmit queue are empty, throw an interrupt. And then a useful one, UDRIE0, which says enable the interrupt when the first of the output pipeline is empty. These 3 bits are related to multiprocessor. I don't want to talk about them right now. So, when you do a put car, in other words, when you use printf, what put car does, the only thing put car does is to wait until UDRE0 is set, and then set UDR0 equal to the input character. That's all it does. It is blocking. It drops into the wait loop. It hangs there until the last character is sent, and then it loads a new character. Get car does a bunch of stuff, but the basic functionality is that it waits until RXC0 is set, and then set some character equal to UDR0. In this version of C, now, I sometimes write my own version of get car and put car because I have better control that way. But, and for the, did any of you try out the interactive shell in tiny real time? I wrote a shell for it so that you bring up a command prompt, you can turn on and off processes and do all kinds of bizarre stuff. And because I disabled interrupts in the command shell, I had to have a version of put car and get car that did not depend upon interrupts, so I wrote my own. The get car by default also does some checking for backspace so that your code doesn't have to worry about backspace, it just works, and it looks for enter and a few other things. But it's also blocking, which means that scanf is blocking. So in past years, when students have, as part of the exercise, I had students write the non-blocking code. That you could do it in two ways. One is you write a state machine that, among other aspects of following through all the states, polls the done bits to see if the data has been received or not. But a much cleaner way is to write an interrupt that just waits until there's a character there. So in tiny real time, I tried to make this as transparent as possible. So I modified put car and get car directly to be interrupt driven. And as I think I said before, put car doesn't take much modification. It's predictable. You know how it's going to work. It's going to take a millisecond per character. All I did was to build a big circular buffer and to run put. So when you do an fprintf, put car actually writes to a circular buffer, and then the circular buffer commands turn on the transmit interrupt and do everything through transmit interrupt, but that's all hidden. And get car simply throws a semaphore and waits until the user does something. So get car, which can wait forever because humans are so slow, just relinquishes control over the process, relinquishes control to the operating system, and then the operating system does what it wants until the slow user types something, and then this process gets control for some small amount of time. So, but there's another version I wrote before this, which is maybe a little more transparent. And in this one, you couldn't use put car, you couldn't use printf, and you couldn't use scanf because the user software was building strings and sending strings. So there was a buffer you had to use, which was loaded by a, well, there were two aspects to this. One was when you were ready to, when you wanted a string from the keyboard, you had to do a get string command, and strings were the only thing supported. And this was non-blocking because all it did was to tell the system that the receive was not ready. You're asking for new input, so it tells the system that you're not ready. It sets some receive index to 0, and then it turns on UCSR0B gets or equaled with 1 shifted by RX CIE0. So it turns on the receive interrupt and then ends. So all it does to initialize a receive is to clear a buffer, clear a ready flag, and turn on the interrupt and wait for the human to do something. Then many, many milliseconds later, so this has the bulky title USART 0 RX vect and of course if we get here it means that there is a successfully received character. That's what throws the interrupt, and so we say that our car, the newest character to come in, is equal to UDR0, which is guaranteed to be ready to read. And then optionally, if we want the user to be able to see what they typed, so if the user is a machine, you don't do this, but if the user is a human, you do this, you set UDR0 equal to our car. That echoes the character back out over the system so that the human can see it, but obviously if you have a machine reading it, you don't. Yes?
Yeah, so you have mentioned for the UDR data, there's actually two offsets, when it's read LA, when it's write LA.
That's correct.
When you write code, you see the compiler will know which UDR data you have.
That's correct. It'll do the right thing. So if you ask to read it, it'll read from the correct spot. If you ask to write it, it'll write to the correct spot. And I thought it was a good idea to be able to handle backspace also. But the most basic thing is, how do you know when the boring user is done? You know when they hit enter. So the very first thing we have to say is, if our car is bang equal to quote / r quote, oh, that's Unix for the enter character. Is that the enter? And if it is not the enter character, then we want to find out if it's a backspace character. Again, you probably wouldn't put this in unless it's a human on the other end of the link, because you're not going to have a machine doing backspacing. Yes.
Is it only limited to use /r, or to use the hex value of that?
You can use the hex value also, whatever it is, 13.
Yeah.
Decimal 13, I think. So then we have to say, we have to find out if our car is equal to quote /b, and if it is, we have to handle the the backspace, which has to do two things. It has to erase a character on the screen, and it has to erase a character in the string that you're building. So we do a put char blank, put char tick \b, and then decrement r index. So that's supposed to be minus minus r underscore. Otherwise, if it's a valid character, then we're going to say r buffer of r index plus plus is equal to r char. And if the human actually, now this is the else that matches the carriage return. If the human actually pressed enter, then we have to do a put char quote \n new line. Have to set r buffer of r index to 0 to terminate the string. Set r ready to 1 and turn off the receive interrupt. UCSR 0B is XORed with 1 RXC IE 0. End the if block and then end the interrupt service routine. So, yeah.
Why do you need the two profiles for that?
So you need to erase the character you just wrote, and then you have to move the cursor back one. \b moves it back one. It worked this way. I tried it both ways. This is the way it worked. What can I say? You can get very complicated. The interrupt service routine for receiving a character can be very complicated if you have other special characters, like Control C to stop a process, for instance, in Unix. What?
Some sort of a prompt that you want to catch.
Or some sort of prompt you want to catch, or a fork command, or whatever happens to be. So what do you think? Next year, should I have people write their own receive interrupt service routines? Or should I?
Something way worse.
Oh, you're kind and gentle.
Make an upside down, buddy.
Draw smiley faces on the. So, by the way, you know that that you can do cursor manipulation in this term in PuTTY. So you can do a screen layout which includes forms in PuTTY and have the cursor move to a certain point on the screen and draw there. You know that? Because PuTTY emulates a hyperterm, which emulates a VT100 emulation, which emulates a real VT100, which DEC invented maybe in the 80s as a general purpose green screen, which was a physical thing. It was a CRT monitor about this big that you set on your desk, and that's all it did, folks. It gave you, it received characters from a remote machine and put them on the screen. But it was novel because it had defined about 50 escape characters, which allowed you to move the cursor and do other interesting things, including draw graphics. So you can do graphics in PuTTY if you want really low quality graphics. But you can do it. Don't see many VT100s around anymore. Well, I'm sad to say the last one I saw had been dropped 7 stories down the Theory Center stairwell.
Just accident.
I doubt if it was an accident. It sure did break it to pieces.
I have a question.
Yes.
Is there a way, if you have 2 black boxes, two MCUs that's communicating with each other, to figure out what baud rate they're using without setting it up?
Yes, you can. So, can you make an auto baud?
Yeah.
And the answer is yes, you can, by guaranteeing that characters are fairly far apart.
Yeah, exactly. But if we're talking about 115200,
So let's say that you type slowly. I used to have a terminal that would auto baud. You plugged it in, and you type slowly on it, click, 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 and after about 10 characters, it knew what the baud rate was. But you could do that as long as there is a space between characters. As long as you're not going at full character rate. So even at 115200, if you're sending a character and then waiting a character time, then sending another character and waiting a character time, and you do that a few times, the other system can figure out the baud rate by the length of the pulse.
Couldn't you also set up like a package structure with a certain start character string, and then keep guessing or keep incrementing, intelligently based upon the pulses, until it found a baud that actually had the same string?
Yeah, well, that you could do too. So you just, if you say there's only 10 common baud rates, then in 10 bytes you can step through them all. So why not do that? And then people do that also, yes. So what if you were going to set up a wireless link? Let's say that you were going to set up a wireless link so the 2 MCUs could talk to each other through the RS-230, through the UARTs. So you have a transmit line. It's connected to the radio. So you have a transmit line. So now the MCU goes out to some sort of transmitter. And then there's a receiver over here which is going into the receive line. And the cheapest receivers you can get, on the order of $3 or $4 each, send a burst of energy if you have a 1, and they send nothing at all if it's a 0. They're turned off. It's called, yeah, it's painful to think about, isn't it? This is called OOK, on-off keying. It is a very primitive form of modulation, but it's really power effective because when you stop transmitting, the transmit power goes to 0.
So is that a form of FSK?
No, it's not frequency shift, it is amplitude modulation. So the receiver now looks at this. We used these kind of transmitters for years in here before one of my students finally figured out they were illegal. We're using it at 434 megahertz. That's a legal transmit band for control in the U.S., but is not a legal transmit band for data. And so we were using them illegally, even though they were cleared for use on 434 band, 434 megahertz. They weren't cleared for the use we were putting them to. But you, yeah.
How exactly would you get caught? Like, who controls the airwaves?
The FCC in their truck, and the guy with the pinstripe boots stomps down the door of the lab and says, "Freeze!"
I suspected it was something like that.
Yeah, that's what happens.
How do they know?
Every time. No, it's pretty hard to get caught with milliwatt transmitters in a shielded building, which this effectively is. Nonetheless, this is not about whether we're going to get caught.
Moral principle.
It is that I can't ethically teach you to do something illegal. Right? That's the problem here. And so, now if you go to 960 megahertz, 918 megahertz, it is completely legal to use an on-off keyed transmitter to send data, as long as you don't go over 1 milliwatt. So, now the receiver here, the receiver might be receiving a 1. If it doesn't receive anything, is it receiving a 0? Or is it noise? If it receives a 1, is it receiving signal or is it receiving noise? And so the way the receiver works is that if it's getting 1s and 0s, it turns down its gain until it gets about half 0s and half 1s. If it doesn't see anything, it turns up its gain until it starts seeing half 0s and half 1s. And that means that if there's no transmission going on, it sees noise just fine. All right. So now in this case, so you have to, there are several steps you have to do here to synchronize the transmitter and the receiver. The first is to do what you suggested, which is to send a series of 1s and 0s, balanced 1s and 0s. You send a series of these, usually something on the order of 3 bytes worth. So you send 0xAA, 0xAA, 0xAA. That will set the receiver so that the gain is approximately correct, because it will have seen a whole bunch of 1s and 0s, and so it'll set its data slicer to the correct level. At that point, this modem is totally, or this UART is totally confused. Where's the stop bit? Where's the stop bit? Start bit? You know. And so the next thing you have to do is send 10 stop bits. Stop. I mean it. Stop. 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 Okay. So you have to send 10 stop bits, and it guarantees that no matter what state the UART is in, you will have cycled it through to a stop bit. So now you have to send 0xFF, which is 10 stop bits, right? Yes.
The receiver lower gain, or lower gain.
It does call it, but as long as you only send 1 byte this way, you're okay. The time constant is on the order of 2 or 3 bytes.
So what happens if you just happen to have data that has a lot of noise?
Good question. What happens if you have data that has lots of 1s and 0s? You can't send that. and yeah, well, no, but this is serious. And so the next thing you have to do, I mean, then typically after this you can have payload, right? But you have to make sure that every byte has an equal number of 1s and 0s. That means, you can work this out, that means that every byte that you send has to be converted to 2 bytes, because you can guarantee, obviously, if you send 4 bits over here, any 4 bits, you invert those 4 bits, put them in the second 4 bits, and you're guaranteed to have a balanced transmission, right? And if you're clever about it, you can actually choose them. I worked out there are 70 possible ways of doing this. You can work it out so that you can always tell the first half byte from the second half byte. But you have to convert 1 byte into 2 bytes, because you can always choose enough redundancy to get DC balancing then, and then you can send an arbitrarily long sequence of ones or zeros and have it work. And the receiving code then has to be synchronized to know which is the beginning and the end, which means it's really nice to be able to tell this byte from this byte. So choosing your codes carefully is useful. You can buy OOC keyed transmit receivers for about $5 each at 916 megahertz. They're quite cheap. My intention in the coming years is to build FSK, frequency shift keyed transceivers, because they're much nicer. You don't have to worry about non-existence of a signal. Does not mean a zero, it means non-existence. With frequency shift keying, you're either sending modulation that looks like this or modulation that looks like this. And you can build those for about $30. Be a good final project. Again, I'm trying to get you to do my work for me. Right? So, I have a request for talking about accelerometers. What do you want to know about accelerometers? Tell me what you're interested in knowing about accelerometers. I mean, accelerometers obviously measure acceleration, and that's slightly deceptive because you take an accelerometer. Let's say that the acceleration axis it's measuring is horizontal. You tip it up like this, it reads -1 because it's accelerating. Because as we know, the equivalence principle says that standing still in a G field is the same as accelerating in free space, right? Turn it this way, it reads +1. So an accelerometer is also a tilt meter, right? Is that the kind of stuff you want to know about? Or you want to know about output codes? Yeah. Communication? Okay.
Yeah, data interpretation.
Data interpretation, all right.
Also, can we talk about SPI mode?
Yes, I will talk about SPI communication. I will try and talk about I2C, but I know much less about it than SPI. I can certainly talk about SPI.
Yeah, for all, some people will be using SD cards. So
yeah, SPI is extremely easy, which is nice. And I will talk about that probably Monday. I'm going to keep talking for at least another week. We do need to, again, I think if you read the assigned readings, you will find that someplace near the end of this month, there are some readings. One is called Synthetic Serendipity. There's a report on the Therac 25 disaster I'd like you to read. Therac 25 was a medical accelerator. This is just to warm you up. It was the first particle accelerator used in medical treatment. So it was 25 megavolt electron beam it produced. And you could either apply the electron beam directly to the human, or you could put it through a piece of tungsten, which converted it to high energy X-rays. And the Therac 15 had been controlled by mechanical interlock switches and a fairly simple state machine TTL logic thing, and it was a pain to use and the operators didn't like it. So for the Therac 25 it was completely computerized. using a computer at the time, which was probably about the same CPU capability as your wristwatch. It was about 100,000 instructions a second. And they took all of the mechanical interlock switches off because, after all, software is always reliable and switches break. The application for this medical accelerator was written in assembler by one guy who had no CS training and who wrote it as a multitasking system and had never heard the word semaphore. And so the system was not interlocked. All of the variable changes were asynchronous. And it was possible for a fairly adept operator, somebody who was typing fairly fast, to put the machine in a mode where the machine thought that it was delivering X-rays, but the physical plant was actually delivering an electron beam unattenuated by a factor of 100. And so the patient could get 100 times the dose that was recommended. 7 people were killed by this thing before it was recalled. And the stories are just hair-raising. The operator turns on the beam and the machine throws an error, but it often does that, so it presses reset and does it again. Throws another error, press reset, does it again. At this point, the operator hears banging on the door and goes over to the door, and they're screaming inside the door, and they open it, and the patient's gotten up off the table and is standing in there with a burn mark on their shoulder, you know, and it's horrifying. I want you to read it.